Hello there, this is Julian again, and this is the second video of the ML hands-on introduction series. In this video, we will be discussing about ensemble techniques. We will explain what ensembling means. We will cover the different techniques that exist, and we will, as before, do some hands-on Jupyter notebooks applying these different mechanisms that are bagging, boosting, voting, and stacking. So first we will cover some theory parts that are very important in the ensembling environment, let's say. And after that, we will go to two different notebooks and see how we obtain a boost in our scores with the NLP with disaster tweets dataset. Let's start. Ensembling means grouping various models in order to obtain better results than the ones we could obtain using a single model. And it's a basic intuition, and while the intuition is quite simple, the implementation of this intuition is not as straightforward as it might seem. Some ways of grouping results or grouping predictions or grouping models are not good enough. They might drop the performance of the models, while others are not as simple as one can think, and where in practice they performed very well, and there was a big, it was an important discovery in terms of experimental results in the machine learning field when these techniques were applied successfully. Basically, there is no theoretical proof or guarantee that these techniques should work, and there was a big time gap between the proposal of one theory. For example, in the case of boosting, the principle of boosting is we can build a strong model using a lot of dummy or very simple models. That's the hypothesis, let's say. And from the proposal of the theoretical hypothesis to the moment where that technique was applied with success, and currently the boosting technique is the best technique that's not deep learning based. All the models, the state-of-the-art models that are not deep neural networks are in general boosting, gradient boosting models. So coming back, there was a big gap of time between the proposal of the idea and the discovery, the experimental discovery of a model that applying that idea works fine. While ensembling is a very large field of machine learning, we can think of these four techniques as the main ones, and knowing these four techniques, we would cover most of the landscape. Voting is the simplest way. Is what comes to mind when one thinks, how could I group a lot of models together? Let's say we have 5 models. So a hard voting technique, let's say we have 5 models and 2 classes, cats and dogs. So we have 3 predictions that say this is a cat, 2 that say this is a dog. Then the hard voting will prioritize the majority and say this is a cat. Soft voting, on the other hand, checks the confidence with which a model proposes its prediction. So if we had these 3 this is a cat prediction, we could see with which confidence. For example, in general, the models are binarized to cat or dog in this example, but behind the scenes, there is a probability. So the soft voting is basically summing up the probabilities predicted by all the averaging the probabilities of the predictions. So if the first model that said it was a cat was a 70% probability, the other one was 80, the other one was 90, and then the other two have a strong confidence in that the sample is a dog, then we could sum up the probabilities of this, the probabilities of that, and compare those probabilities. A slighter, more complex idea is a weighted average, where we could assign weights to each model based on some facts, for example, how well they perform on the data set by themselves. So we would say, okay, I want this model to have twice as many votes as the other, and so on. This is a technique that works with any set of models, and in general is applied in the case where we have a variety of different models and we want them, all of them performing at their best. This means all the hyperparameters of the models were set correctly and they are performing fairly good in and fairly similarly among them. Then this voting technique will boost the score a little bit. We're not talking about a large improvement. We are always talking about the last mile, let's say. This is voting. Follow-up idea of this weighted average or weighted soft voting is stacking. Stacking works with a variety of different models as well, and the idea with stacking is we obtain predictions of, let's say, 5 models, and we have this. This one said this was a cat with 70% of probability, cat with 80, actually, dog with 90, dog with 100, and based on those probabilities, we will train a new model called a meta model that will learn how to predict the output, but not looking at the original features of the sample, but looking at the predictions of these first layer models. So we could have a separate part of the data that we will use to train this model, whose inputs will be the predictions of other models and whose outputs will be the final labels like cat or dog. The problem with this technique is more complex, and the problem we can think of the meta learner as learning the weights of a weighted average somehow. That could be, it's more complex than that because the way this meta learner will make the models interact is more complex than a learned weighted average is a subcase of stacking where the meta learner is a linear regressor, is a linear model. That in that case, each model has a weight associated, each model's prediction has a weight associated with it, but we can put as a meta learner something more complex. In that case, the interaction between the 5 base models will be more complex. And the idea is that this meta learner is a kind of, it's evaluating how good the models perform in different samples. So it will be able to distinguish among different parts of the input space and say, okay, these two models, for example, when these two models agree, then they tend to be correct, and discover that those kind of patterns. The meta learner also can have as input, besides the predictions of these base models, it can have the features, the original features, the first level features as input as well, in order to discover, for example, that model 1 performs correctly when the feature 1 is between some range of values, for example. Finally, there are two techniques that are typically applied on top of a set of decision trees. Although the techniques are generic, the techniques are called bagging and boosting. In general, what's common in the field of machine learning is to apply these techniques to decision trees of some characteristics. And these ensemble techniques are so common and so used that they already have models that implement them and that are more used than the base models. So, to rephrase, decision trees are a very naive and simple models that don't have a great performance. They are interesting because they allow explainability to people that doesn't understand the machine learning, so they have that quality that makes them interesting. But in general, to obtain good performance based on decision trees, we could apply bagging or boosting. And they give a name to two different techniques. One is random forest, and the second one is gradient boosting. Random forest and gradient boosting decision trees. The techniques are not as straightforward as voting and stacking, and have some interesting insights in them, and they are kind of opposites. So in bagging, what we could do is we will take very deep models that overfit the training data. They are too smart for the data they have, so they kind of learn the data by memory, but they are not good at generalizing. So we take those models that are too complex and they just learn by memory the full training data, and what we will do is we will fit those two smart models to different versions of the data set. So they will learn too much of different views of the data, and with a bunch of those models, we will average them, with the hope that averaging them will reduce the overfitted error. And it does happen, and it works very good. So in this case, the base models are decision trees that are very deep, and they do something that's called overfitting. This is a central concept in machine learning, and we can see that there is the problem of underfitting and overfitting. Probably you have heard of it. So let's see this with an example. This is the samples, the data. This is the generator function, and we are feeding a model. That's the blue line. In this case, the model has not enough freedom to fit the data. We are saying we can model this data as a line, and the data is not aligned, so the line fits as good as it can, but it's not good enough. So in this case, the model is too simple and it's not good enough to fit the training data. So it will have low training accuracy and low training score and low validation score. It won't be able to fit the data it sees, and it won't be able to generalize to data it hasn't seen yet. Okay, on the opposite end of the spectrum, we will have a model that's too smart to for the data it's feeding. In this case, it's a polynomial with 15 degrees of freedom, and it's able to fit the data perfectly, the training data, but as it fits the observed data this perfectly, it's capturing noise, basically. It's overfitting to this specific data, and it's too smart to recognize that actually it's a simpler line, that's what's generating the data, a simpler line with some noise. So in this case, we will have a perfect or a very high training score, whichever metric we are using, but we will have a reduced validation score. What we want is the in-between situation where we have enough freedom to fit the data without overfitting the data. What we will do with bugging is overfit the data, but we will show the models. The decision trees are known for overfitting because they can just keep making decision trees are models that have branches, are the common decision trees, and there is an algorithm to fit that. In general, we use binary decision trees. This is each branch can ask one question to one feature, and the answer should be yes or no. So this is a binary simple decision tree, and there is an algorithm that has in each step knows what's the better question to ask. It's the question that better separates the training data. So with this fashion, what you can do is keep asking questions till you fit the data perfectly. If you allow the tree to be as deep as it needs to fit the training data perfectly, it will eventually reach a perfect score on the training data, but leaving to regions of the input dimensions that are not generalized. Bugging takes this fact and exploits it. What will it do? It will take the data set and show, let's train, for example, 1,000 decision trees with infinite depth in potential. But each of these trees will see a different part of the data set. We will do something that's called bootstrapping. We can think of this, it's a more complex version of taking 90% of the data set and taking, you have 100 samples, you could take 90, and that's one version of the data. Then you put back the 100 samples and you take 90 again, that's the second version. And you keep doing this, you generate 1,000 versions of the dataset, and you fit one overfitting model to each of them. And then you average the results, the predictions of each of these 1,000, with the hope that averaging this will cut off the variance, the unneeded extra variance that each model has, and will keep the generalizable aspects of each of them. This works fine. This is a model called random forest, and is one of the best performing models of non-deep learning nature. Boosting, on the other hand, is the other ensemble technique based on decision trees. With boosting, we will finish covering the 4 main techniques for ensembling. And boosting is the current technique that generates the best results with non-deep learning models. So if you take a model that's not a deep neural network, in general, the models that perform the best are boosting-based models. So this is the state of the art of machine learning nowadays. There are random forests come in scikit-learn, gradient boosting trees come in scikit-learn now as well, but there are 3 libraries that implement them, variations of them. This is extreme gradient boosting, light gradient boosting machines, and cat boost. There is the command to install them here, and they all offer the same interface as scikit-learn. They integrate with scikit-learn perfectly, and this is what you could apply out of the box in order to obtain results fast. You could try with these 3 guys right after pre-processing your data. What does gradient boosting? There are two different mechanisms of boosting: weighted boosting and gradient boosting. The boosting idea is, can we take a lot of dummy models and build a strong model with them? And the answer is yes, and this is one of the mechanisms that implement that concept. What we will do is we will take a lot of dummy decision trees. Instead of allowing the max depth that could allow the model to overfit the training data, what we will do is have very short decision trees. It might be a 1 question decision tree, like is this feature greater than 0.5, true, false, whatever. The only condition that should be met is that the predictor is slightly better than chance, than randomness. So it should have an accuracy greater than 0.5. Let's say it's I think it's AUC rock above 0.5. I don't remember, but the idea is it should be slightly better than chance, and we don't want much more complex models. We want very dummy models, and we want a mechanism to group them together and see if we can get a good model. What we will do here is gradient boosting is going to do as follows. First of all, it will train a decision tree, a dummy decision tree, on this is a data set of 4 features and the target. We will feed, the first model is a normal decision tree fed to this data, and here are the predictions. Okay, it has some predictions, they are not great. Actually, here in this column you have the error. The first prediction has 0.2 of error, positive 0.2, 0.25, 0.35, minus 0.4, minus 0.55, and so on. The second model of our ensemble will not predict y, it will predict the error that the model 1 had. This is the y, the label that the second model is trying to guess. So given the task that the second model will address is, given these 4 features, predict the error of the first model. Okay, that's the main idea of boosting. Now what will we do? We will combine the prediction of the first model plus constant times the prediction of the second model about what the first model mistakes were. Okay, so we will kind of sum up, but the second model will have a small percentage of the weight. Okay, we will have the prediction plus minus the estimation of the error that the second model did. That will be our second iteration model. Model 1 plus alpha times the prediction of model 2. And what this second term is doing is trying to correct somehow the prediction of model 1. And now we will fit a third model, which will predict the error of these two ones associated, ensembled in this formula. We will have this prediction, and we will add it with this term that end up being an exponential formula. Each model, the first model adds more, and the second one it's exponentially decaying. The addition each model provides is exponentially decaying with the number of iterations. This procedure performed a lot of times will reach a very good model, which are the state of the art nowadays in non-deep learning models. There is another boosting technique named weighted boosting. This is gradient boosting. The name comes from a fact that this is a kind of an approximation of gradient descent. But it doesn't matter. This is the main idea is let's group together with this technique a lot of dummy decision trees of depth 1 or 2 or 3, very small trees, and the performance of the first model is not great, but in the end, adding 1,000 of this with this fashion is going to get great results. So let's jump into the notebooks now. Okay, let's start with the code now. I have written 2 notebooks that we will use that are available already in the GitHub. Let me check. They should be here. The names are Ensembles, bugging and boosting, Ensemble, soft and hard voting, and there's also a third one that we will discuss about it later. That's transformers hard voting. Let's start with bugging and boosting. Here, the title is incorrect, it's the old one. Here are the summary of the previous video, the results we obtained that were 79.5 in the validation accuracy, 78 in leaderboard. This is the best. This is the best cross validation, and this is the best leaderboard. The models were quite similar. There were logistic regressions on top of 5,000 words. One used PF-IDF and the other used count vectorize. Here, all this code comes from the previous notebook. It's just wrapped up for loading the data frames. And here we are using some new code. In this notebook, we will see decision trees and the four most common models that are built on top of them. This is random forest classifier that comes from scikit-learn, and these three gradient boosting models that come from different libraries. This one is owned by Microsoft, this one is from a Russian company, and this is specific for this library. This one was the first gradient boosting that was the state of the art, and then these two came. Light GBM is faster and has a reasonably good performance, while Cat Boost is slower and performs on the same level of XGBoost. Here we define two simple functions. One is run, which will fit the model to the training data, get predictions for the training and predictions for the validation sets, and then calculate the accuracy for both sets and return the fitted model and the accuracies. And run models is going to call this function here, line 16, for each of a list of models, and then we'll group the results together in a data frame. Okay. You can see that we are calling the fit model with the text, the unprocessed text. In order to do this, we are using pipelines. Pipelines are some handy scikit-learn objects that allow us to build a lot of steps of pre-processing plus prediction steps all together as one single model. And the pipeline knows that, for example, when calling fit, it will fit each of these objects. For example, let's see this pipeline. This is a first, it goes a TF-IDF vectorizer, and on top of that, there goes a decision tree classifier. When calling predict, it will apply the transform method of all the steps before the model, and then the predict method of the last object that should be a predictor. Okay, so that's how we can call the model with the text and not with processed vectors of numbers. Okay, so here we define a decision tree pipeline. I don't know why they are different. That's better. Three gradient boosting pipelines, one with LGB, one with XGB, and one with Cat Boost, with 1000 base models. And finally, we define a random forest classifier. It takes a while to run because the input size, here we are using max features instead of providing the vocabulary by ourselves. We are asking the model, the vectorizer, to select the most common 3000 words, dropping stop words. We will see the results might change slightly, but not that much. And we will see that in general, all the ensembles are in the same range, while the decision tree, the standalone decision tree classifier, is much worse. One note here is that decision trees are good for tabular data. That's not text data. For text data, deep learning models took the lead long ago. Deep learning is still non-deep learning models are still competitive in tabular data, but for images and for NLP tasks, deep learning took the lead long ago. So in this scenario, and in particular in natural language processing, the models that work fine, okay, here we have 68, we can see that with ensemble techniques, we have a boost from 68 to 74, 75, and even 76. You can see also that this in the training dataset, the models have very good performance. This means by the very nature of all of them, they are overfitting the data. So here what we want is to work fine although the overfit happens. We will not submit these models because you can see that even the ensembles are not as good as single basic logistic regressions on top of count vectorizer. And I was saying before, logistic regression and naive Bayes applied on top of TF-IDF or count vectorizers are very simple models that work very good as baselines in NLP. So what we did on the last video was very simple, yet as good as it gets with non-deep learning models for natural language processing. So these models don't look that good here, but they might work very good in just tabular data. And we will jump to soft and hard voting with logistic regression and naive Bayes and other model named SVM that is known to work fine on NLP tasks. And we will finish showing how state-of-the-art transformer models grouped together with a simple strategy reach a very competitive position. Actually, with the current leaderboard, grouping 5 models, we are possibly 1, 2, 3, 4, 5, 6, 7, 8, 9th in the real leaderboard, 9 out of yeah, we are very well positioned. So let's see these soft and hard voting mechanisms. This is a copy paste. This is the best in the validation set. We are putting CV because it's the standard use. It means cross validation. We are not doing cross validation. We are doing just validation, but this is how you will see results in CAD. So we had, this is the best score we obtained with a single model in cross validation, and this is the best score we obtained with a single model in the leaderboard. This is all the same as the previous notebook, okay? And here the models we are running are one naive Bayes on top of a count vectorizer of 1000 features, the same as one naive Bayes on top of 3000 features, 3 different logistic regressions, and one support vector machine. With these 5 models, we obtain better results already than the ones we obtained in the previous notebook. Why? Because we are letting the count vectorizer pick the vocabulary, and therefore some stop words are dropped. The vocabulary is generated with much more thought put on it, and therefore the features are more informative, and that's why we already had a boost here. We can see, for example, we can distinguish that the SVM is the one that's overfitting the most. It's not overfitting necessarily, but it's going in that direction compared, for example, to this one that's growing better together. Now let's do an average of this. Let's do it manually. We have the models, and I will break here. So one proba, we can ask probabilities to the models. This one, for example, is the prediction of the first model, and we are asking for probabilities in this case. The first model is I don't remember. Oh no, hold on. It's overridden by the code executed below. Let's run it again. It will take a moment. In particular, the SVM takes a while. Here, the one that took the most was the cat boost, and in this case, it's the SVM. But in general, all the models have this predicted proba, which will show us the underlying. That's it. The model is a pipeline. Let's see what's inside of it. In steps, model. The model is a multinomial naive Bayes, and we are asking this model to get the probabilities. The model.predictProba returns a this is the amount of validation samples. There is one prediction per sample, and for example, for the first sample, it predicts 68% of chances of probabilities of being of class 0, and 31, this is the complement of being of class 1. Therefore, and here what we are doing is taking the probability of class 1. This is the probability for all of them. So here the 0 is the 31% probability of being of class 1. We go over all the models, getting the probability for being of class 1 that each of them generates, and we sum them up all together. We are taking the average, basically. We sum the probabilities. By this moment, we will have, since we have 5 models, this will be higher than 1. It might be higher than 1. It's a number that's between 0 and 5. It's not a probability, it's the sum of 5 probabilities. That's why we divided this by 5 in this line. Okay? So that way we obtain that this guy has probability 39 of being a disaster tweet. Finally, we threshold this. This is the normal threshold. We can change this number. In general, 0.5 is used. Actually, we can change it right here and see how goes. Okay, actually that did pretty good, right? Let's submit this. It increased. Let's submit this and see how it performs, because actually 82 point something is something that I couldn't get with the ensembles, and it's quite high. So let's see how it works. Let's do a live. It was 67, right? With fresh. You can fine tune this, right? Manual average, fresh. What's this? Oh, okay. So yeah, we need to do the prediction with this. We need to do this for the test. I will upload this modified version soon. That's it. Let's submit this. What was its name? It might be overfitted to the validation set. Let's see if it's better than the best. Okay, so it is, since I handpicked, when I handpicked the value that was the best on the validation set, I was kind of overfitting to the validation set. That could be that's a data leakage, and it's the number that worked best on the validation set. Everything was seen because the model, that's the group of the models plus myself, all of us, we have seen the data because I have seen the data, and I handpicked the one that performed better, and therefore that number was not necessarily something that could generalize, right? But anyway, we can try. It might be good, but it wasn't. We can see, we could check what happened with this, the previous one. Let's see. Let's do that. It might be over, it might be worse, but it might be just better. Not that great as after the final ensemble, but good enough. Let's submit this as well. The question here is the 5.7, it did improve? Yeah. So all my previous argument is not, doesn't apply. Although it's an obscure mechanism to handpick this, if it works, it just works, right? With these caveats. Okay. So this voting was a soft voting that can be done by a voting classifier with the parameter voting equals soft. And you can see that this 80, 83, 99 is the same as, where is it? As this one. This should give the exact same number. Okay, There is a round here, so this 98.9 is 99. This is why? Because it's the exact same mechanism grabbed by this voting classifier. The soft voting is the same as an average of the probabilities predicted by each model. A hard voting, on the other hand, is getting the binarized version and make them vote as one. Each model counts as one vote, and they vote, so it's integer numbers. And you probably want to have an odd number of models, so they can break the tie in that case. And we can see that the soft voting performs slightly better than the other one. On the other hand, we already have gotten a better result than the best we had with our submissions. This was the best model that we had with single models, 919, this one, and here we are here. Okay, let's move on. I couldn't get much better than this. The type of models that are being assembled, we are already fighting against a ceiling for non-deep learning models here, and we will feel it. The improvements are important, considering, for example, that the base was 657, right? This was a very cheap model. And so we are moving in, 1 second. The range in which we are moving is, let's do it here. Let's close this one. We are moving in the range of, let's say this is a very basic base, and this is where we are at right now. So the range is this 13 points, right? And we obtain one, let's be exact here. Let's say that this model is a super basic baseline, and we will reach by the end of this video this number. And the best we could achieve with single models was this number. Improve sampling, full range, best model, single model. Best ensemble model, and what we want to see is the, let's do various numbers here. Ensemble minus single divided by the full range. Sorry, parentheses here. Okay, 5% of improvement over the 5.5 over the total range, which is, it's something important. more considering that we are already saturating all the signal that these models seem to be able to capture. So the ensembling technique will not get much better. Another mechanism is a weighted average. Here we implement it by hand. We assign 5 weights and we multiply each prediction probability by the weight. And since the total now it's not the amount of models but the amount of weights, we will divide by this addition of the weights. And that way we will, let's see if this number is still something. It is. We might actually get a better score now. Let's try this. It's this one. This line, this line. Actually, let's do it with the best model I got before. So this is a way to do a weighted average, and the same exact result, exactly the same. 8, 1, 2, 3, 3, and this is a 6, can be obtained with this weights parameter here in the voting classifier. This is exactly the same code. Finally, we have this ensemble. That's what, after trial and error, I found to be the best performing one. Note on this is the following. This trial and error is done over the validation set, which means that the results obtained on the validation set are not longer a good estimation of the predictive power on unseen data. Why? Because of my part of the process. My part of the process, on the other hand, could have been done automatically, right? So, for example, let's take as an example this tweak of the 57 instead of 50. This could have been a for loop trying different thresholds until we found the best number. And this procedure is as good as fitting a model, right? It's a valid procedure. The problem is that now the data we have prepared for validation is contaminated. But we can fix this with a train, validation, and test data. We are not doing this because currently the leaderboard is somehow working as the final judge of our predictive power. Using the leaderboard, submitting, doing a lot of submits and overfitting the leaderboard is also possible, and it's a problem in competitions. For example, there is one competition that's going to end in 2 days that has a leaderboard that has only 5% of the test data, and people discovered how to overfit it. Actually, there is code that's by trial and error. There are something called scaling, which is a silly thing that's modifying the test, the submission scores, with random numbers. These numbers are put by trial and error till it improved the leaderboard score a lot. And we are expecting a very large shake-up due to this. And for example, in my case, for example, I didn't pick the best performing public score models. I chose models that I trust more for submission. I put this one that's only a linear model, and I chose this one that's an ensemble that I build that I trust. And that's not, it's hopefully not overfitted to the leaderboard. Coming back, it finished. And so this is the only comment. If we are going to fit hyperparameters in the validation set, we need to have a separate, the most clean mechanism is to have a separate test set that's never touched, is not used for these things, and is used for assessing the generalization power of the model on unseen data. Though that split in three parts is what's commonly done, and the process of fitting, for example, the weights, deciding these parameters, deciding this number, and so on, is called hyperparameter tuning. The models are trained on the train split. The hyperparameter tuning happens on the validation set, and the predictive power is assessed on the test set. So coming back, it already ran. This model is the best I could achieve by hand, trying different models, and on the leaderboard it's scoring this guy is this guy. Okay, now we will submit this is the best model I could get ensembling this kind of models. Let's do a, how can I do this? Trend model. I think that estimators. Okay, so for model in estimators, let's do this. This comes here, but this is the test. There are no weights. What I want to do is get this guy and threshold it with 57 and see if that performs better on the leaderboard. What's this threshold? This 57 is we are being more picky of when to say that a tweet is a disaster tweet. Okay, that's what it is. Divided by length. I think this should be. I think it was a name, comma model, and we will not. Let's do this. Let's set the validation here, right? And this should be this number. We are expecting this accuracy to be not fitted inputs. Hmm. Hmm. Get Windows get detailed estimators. I would like not to. Okay, hold on. This might be. I think this could be it. Yes, but something's broken. Okay. Oh, this waits approval. Good. This is great. We did it. So now let's try this threshold here with 57. It decreases. 55. It increases partially. 6. 53. Yeah, here it doesn't look like it will increase a lot, but let's give it a shot with 55. BF test. And what was the submission? Where is it here? Beth with manual fresh 55. Okay, let's submit this. I hope we still have submissions, 2 more today. Best with manual. Let's see. So the best we had till now is this. So hopefully this will go better and achieve .8. Let's see. No, and it went down actually. It went down a bit. Okay, we couldn't do that. That's okay. It was an experiment. And okay, now what I want to show you is a final experiment. So here we are reaching the what seems like the ceiling for me of non-transformer models. Possibly all these guys are BERT-based. This is transformers. This is deep learning models. Okay. This is BERT with TensorFlow. We are 79. What was that? 8 here. It's not great, but it's good enough considering these models. Now, I have different submissions that we can explore in how they were done with transformers. These are old ones that I did while I was studying. There are some Robertas, some BERTs, okay? And this is what I did today, an hour ago, hard voting. So I got my 5 best performing submissions. I don't have the code that generated them, so I can only do hard voting. I think that with soft voting, the score might get even better. But I make them vote these 5. It was an odd number, the ones that are above 83. So that was great. And here I download the CSVs. I loaded them. Here is the data frame with the 5 models saying 1 or a 0. And I sum them up here in the column votes. And basically I did, if votes is greater or equal than 3, then it's, let's do this as well. I guess this is going to be too much, but let's give it a shot. Yeah, this is going to be too much. 3.5 would be great, but we don't have that kind of detail. We are moving. Okay, it was the same as the single one. Anyway, with this hard voting, I was able to get a very slight improvement from the previous model, but this slight improvement led to this position. Position 46, this is the, and we can see that, oh, well, the single model is here, right? That was the single model result. Yeah, so it wasn't that much, but it did some improvement. At this point, these numbers start to count. You can see that we are working on the 3rd decimal mostly. These guys are probably cheating. This guy, I cannot tell. What I know is that here in the public code, that's not cheating. This is the first model that's public here, public from the origin of time, has this score. This score, 85. This is a reasonable ceiling to think when we think about, because why? Because I assume that a better score should have been published eventually in, I don't know how long has it been going, but it's been a long time. It doesn't have dates, but it's been here for a while, this competition, and there is no 88 model published, and that would get a gold medal, so someone with that model should have published it. Anyway, we are discussing about one position. It's important though, because it scores almost 4 points more than the following one, but we are 1, 2, 3, 4, 5, 6, 7, 8, 9 in the leaderboard right now with this simple ensemble technique. We can eventually do another follow-up video discussing about these models, and we have seen ensembles in action. We discussed about decision tree ensembles, bugging strategies leading to random forest. This is over a lot of overfitted models on different versions of the data set being averaged in order to reduce the variance, the overfitting, the excessive fit to the training data. We discussed about boosting. We discussed about how with this strategy of correcting the error of the previous model, we can do a chain of dummy models that in the end reach a strong model. We discussed about stacking, how a meta learner can learn to predict the target based on the predictions of other models as features. And we discussed about soft voting or average of confidences, hard voting, weighted averages, and with that we had covered the full landscape, or the most important parts, like the 90% of the landscape, the mainstream of what's ensemble techniques. I hope this was a clear explanation, and that's it. Bye bye.